Lesson 11.6, Image Formation by Mirrors. A concave mirror bends in. A convex mirror bends out. Examples. A concave mirror be like the inside bowl of a spoon. The convex mirror be like the back of the spoon. Concave mirrors are makeup mirrors, are concave mirrors. Convex mirrors are like some old stores. You can see these round mirrors that you can see around corners with, or maybe the outside of a shiny sphere. Anyway, concave mirror is concave mirror is converging. The rays of light come in and come towards the middle. A convex mirror is diverging. Rays of light come and go away. Normals, as the term implies, are always perpendicular to the surface and pass through the center of curvature C. C takes the place of 2F from the lenses. The law of reflection states that an angle to the normal is the same for the incident and reflected rays. So you have a ray coming in, it hits the mirror and reflects at the same angle. The principal axis is an imaginary line through C in the center of the mirror. The focal point, F, is the place where parallel rays strike the mirror and converge onto that single point. The focal length is the distance between F and the mirror. So for a concave mirror, that would be 1/2 the radius of the mirror. R is the radius. The point would be C. For a convex mirror, since it's on the wrong side of the mirror, where it doesn't truly exist, we'll say it's a -1/2 times the radius, or -1/2 the distance to C. Spherical aberration is the rays far from the principal axis actually cross between F and the mirror, like in this picture. We fix this by using a parabolic mirror. So if you have a flashlight or your car headlights or whatever, the reflector is usually more parabolic, so you can get a nice tight beam. If you don't, then it's spread out and doesn't really focus at a single point. Our ray tracing diagrams is a diagram used to find the location and type of image produced. We did that the last lesson with lenses. For the mirror, it looks something like that. Wow, it looks kind of complicated. But hey, let's run through it step by step. Notice all the rays start at the top of the object, and where they cross is where the image is. So for a concave mirror, there's our mirror, there's my center of curvature, and there's my F, and yes, I truly really measured it all and found where the center of the curvature was and halfway between that. Mirrors are a little less forgiving than lenses. Lenses are easier to draw because we just went to the center of the lens. The mirror, you have to draw it really nicely to get this to work. It has some object. I'm putting it way out there. Ray 1 is parallel to the principal axis, strikes the mirror and reflects through F. So it goes parallel, hits the mirror, and reflects through F. So that was ray 1. Ray 2 goes through F, strikes the mirror, and reflects parallel to the principal axis. So it goes from the top of the object, goes through F, and hits the mirror. So this is ray 2. It reflects back parallel to the principal axis. So that's ray 2. Ray 3 goes through C, strikes the mirror, but since C is the center of curvature, this is like a radius. It's going to be perpendicular to the edge of the circle, so that means it comes straight back. So it goes and comes straight back. So that is ray 3. Notice they all meet at a point right there, so our image is right there. So when our object is beyond C, the image is real, inverted, and smaller between C and F. Just like we were doing with the lenses, if it's a real image, it's inverted. Let's try another one. If the object is between C and F, so here's my principal axis, there's my mirror, yeah, I kind of extended the top a lot. There's my center of curvature, F is halfway in between, and I put a little object there. Ray 1 starts with the object, is parallel to the principal axis, and hits the mirror. It is reflected back through F. Ray 2 starts at the top of the object, goes through F, hits the mirror, and is reflected parallel to the principal axis. Ray 3 starts at the top of the object and goes through C. Well, C is the wrong way, so we're just going to connect from C to the top there. So you draw a line so it goes all the way, reflects straight back. So that's ray 3. And you can see they all meet nicely right there for the image. So when the object is between C and F, the image is inverted, real, and larger beyond C. Let's do this one more time. Ray 1 goes parallel, reflects through F. Ray 2 goes through F, reflects parallel. Ray 3 goes through C, comes straight back. Let's try another one. This time let's put the object between F and the mirror. So my mirror, C and F. As C, I measured exactly. F is halfway in between. Put my object somewhere like that. First ray hits my mirror and reflects through F. Ray 2 goes through F. Well, for that to happen, it needs to line up with F. So this is ray 2. And it reflects parallel. So that's there. Notice they're diverging, so I've traced them backwards. Ray 3 goes through C. And notice in the real world, on the left side of the mirror, they're diverging. They're not going to meet. So that means the image is on the right side, where if we drew the rays backwards, they meet there. That's our image. Since that's back behind the mirror, it is a virtual image. The image is upright and virtual and larger behind the mirror. That is why we use concave mirrors for makeup mirrors. You get it really close to your face, and your face gets really huge, so you can see everything that's wrong with your face to cover it up with makeup. A convex mirror. You can see what it really looks like in the picture. Took the picture on a playground. Alright, this time the center of curvature is back behind the mirror, so it's the focal point. The object is there. Our ray 1 goes parallel and reflects through F. Only way to get that to happen is if we draw it like that. So remember, it's reflecting away from the mirror to the real world. Ray 2 goes towards F, but reflects parallel. So this is 2. And notice that it's diverging, definitely, so I have to trace them backwards. Ray 3 goes straight through C and back. The 3 rays in the real world, 1, 2, 2, and 3, are diverging, so we trace them backwards over here. Back side of the mirror, there's our image. It is upright, virtual, smaller, between F and the mirror. So in the picture there, notice that myself, my wife, and son all look small. Conveniently, there is an equation, so you don't have to draw pictures all the time. 1 over F equals 1 over DO plus 1 over DI. Wait a minute. That's the same as the thin lens equation. F is the focal length. It'll be negative if it's a convex mirror. DO is the object distance. DI is the image distance. It'll be negative if it is virtual. We also have the magnification equation. Again, it's the same as it was with lenses. M is magnification. HI is your image height. HO is your object height. Image height will be negative if it is upside down. DO is the object distance. DI is the image distance. Again, it'll be negative if it is virtual. So let's say a half-meter high toddler is playing in 10 meters in front of a concave mirror. The radius of curvature of 7 meters. What is the location of his image? Well, let's see, what do we have? We have the object height. We have our object distance. And we have our radius of curvature. And we know it is concave. So if we use the mirror equation, first of all, we need to find our focal length. It's 1/2 the radius. It's concave, so it's a positive 1/2 the radius. 1/2 of 7 is 3.5. Use our mirror equation, 1 over F plus 1 over DO plus 1 over DI. Fill in what we know. We know the DO and the F. Subtract the 1 over 10. Run it through the calculator. 1 over DI is that. Reciprocal that. And DI is 5.38. What would be the height of his image? Well, we could use the magnification equation. We know the object distance. We now know the image distance. We know the object height. We can fill those in. Multiply both sides by 0.5. And his image height would be negative 0.269. Negative? What's that mean? That means it's upside down. And then you think, does this fit? He's further away than the radius of curvature, so he's further away than C. So that was case 1. And the image should be between F and C, which it is. And it should be inverted, real, and smaller, which he is. So it works. Yay! Let's do the same problem, only now it's a convex mirror. So we have our object height, our object distance, and our radius of curvature. Start by finding F. Since it's convex, though, it'll be negative. So it'll be negative 3.5. Put that in the mirror equation. 1 over F equals 1 over DO plus 1 over DI. Subtract the 1 over 10. Run it through the calculator, take the reciprocal, image distance is negative 2.59. So that means it's on the other side of the mirror where things don't really exist. What's its height going to be? Use the magnification equation. Fill in the numbers. Multiply. We had a negative of a negative. Made it positive there. Multiply by 0.5, and we get a height of 0.13. It's positive. That means it's upright. It is smaller, just like we'd expect the convex mirror. I know that was a long lesson. Homework, you can use the equation for most of it. Have a good day.